Welcome to the soundtrack of your scientific realm. This is Yash presenting to you the first episode of the KaleidoScope series of podcasts where I'll be your guide to the world of electronics and help you achieve a better level of clarity. In my first episode, I'll be talking about an upcoming technology called MEMS.
MEMS is a technology that can be defined as miniaturized mechanical and electromechanical elements that are made using the techniques of microfabrication. MEMS are separate and distinct from the hypothetical vision of molecular nanotechnology or molecular electronics. MEMS components vary from 1 micrometer to 100 micrometer in size, and the devices generally range from 20 micrometer to even a millimeter. They consist of a central unit that processes data and several components that interact with the surroundings. The standard structures of classical physics are not always useful at these scales because of the large surface area to volume ratio of MEMS. Surface effects such as electrostatics and wetting dominate over volume effects such as inertia or thermal mass. MEMS are fabricated using semiconductor device fabrication technologies such as molding and plating, wet etching, dry etching, and electro-discharge machining. One of the earliest examples of a MEMS device is a resistor, which was an electromechanical monolithic resonator. The vision of MEMS, whereby microsensors, microactuators, and microelectronics can be integrated onto a single microchip, is expected to be one of the most important breakthroughs of the future. This will enable the development of small products by augmenting the computational abilities of the microelectronics with the perception and control abilities of the microsensors and the microactuators. Microelectronic integrated circuits can be thought of as the brains of the system, and MEMS augments the decision-making capability with eyes and arms to allow microsystem to sense and control the environment. Sensors gather information from the environment by measuring mechanical, thermal, biological, optical, chemical, and magnetic phenomena. The electronics then processes the information derived from the sensors and through some decision making direct the actuators to respond by moving, positioning, regulating, pumping, and filtering, thereby controlling the environment for some desired output. A transducer is a substance or a device that converts or transfers an input energy into a different form of output energy. The pH probe that converts chemical to electrical energy, the molecular electric transducer that converts motion in electrolytic solution to electrical energy, and the fuel cell which converts energy from a reaction to electrical energy are all examples of the electrochemical transducer. The loudspeaker which converts electrical signals to sound waves, microphone that converts sound waves in air to electrical signals, and the hydrophone that converts sound waves in water to electrical signals are all examples of the electroacoustic transducer. The magnetic cartridge that works on the principle of motion in a magnetic field generating electrical energy, and the generator which works on the same principle are both examples of the electromagnetic transducers. Electrometer that converts energy from a vibrating reed into electrical energy, and the Van de Graaff generator that converts static electricity into high voltage are both examples of the electrostatic transducer. The strain gauge that uses deformation of an object and converts it into electrical resistance, the galvanometer that converts electrical current of a coil in a magnetic field to movement, the motor that uses electrical energy converting it into mechanical energy, and the quartz crystal that uses mechanical stress to generate electrical energy are all examples of the electromechanical transducers. The cathode ray tube uses electrical signal and converts them into light energy for a visual output. The light bulb that converts electrical energy into visible light and heat, the laser diode that converts electrical signals into light energy, and the photodiode that converts light energy into electrical signals are all examples of photoelectric transducers. The thermocouple that converts heat into electrical energy, and the thermistor, which is a variable resistor affected by temperature changes, are examples of thermoelectric transducer. The Geiger-Müller tube
converts radioactive energy into electrical energy. Transducers have a variety of application in the MEMS technology. The microgenerator that use micromagnets spin at a rate of 10 to the power 5 rate revolutions per minute, generating 1.1 watt, enough to charge a cell phone battery. And the MEMS hydrophone detects sound generated by ship, submarines, ocean waves, marine animals, tertiary waves, etc. Microtransducers that use temperature, chemical reaction, mechanical stress to produce changes in voltage, resistance, resonant frequency, or light are used in MEMS pressure sensors, temperature sensors, chemical sensor arrays, and optical modulators.
A sensor is a device which responds to an input quantity by generating a functionally related output which can be read by an electronic instrument. Sensors detect by receiving a signal from a device like a transducer. Thermometer, which measures absolute temperature, the thermocouple gauge that measures temperature by its effect on two dissimilar metals, and the calorimeter, which measures the heat of a chemical reaction or physical changes, and heat capacity are examples of thermal sensors. The photodetector that detects light and electromagnetic energy, the photoresistors that measure variable resistance affected by intensity changes in ambient light, and the infrared sensors are all examples of optical sensors. The seismometer that measures seismic waves, and the acoustic wave sensor that measures wave velocity in air or an environment to detect the chemical species present are examples of acoustic sensor.
Then there are a wide variety of motion sensors that work on a variety of principles, like that of infrared that are used in passive and active sensors, those of optics that are used in video and camera system, radio frequency energy used in radar, microwave and tomographic motion, sound waves which are used for microphone and acoustic sensors, vibrational which are used in triboelectric sensors, seismic sensors and the inertia switch sensors, and magnetism which are used in magnetometers. Then there are Geiger counters that detect atomic radiation and the Geiger counter detects atomic radiation and biological sensors monitor human cells.
Application of sensor in the MEMS technology is very extensive. The MEMS barometric pressure sensor uses a pressure microtransducer that converts motion from changes in pressure to electrical signals. These are used in wind tunnels and weather monitoring systems. MEMS chemical sensors are used for detecting gases. These are used in environmental, quality control, food processing and medical diagnosis fields. They are also referred as e-nose or the electronic nose. Biological MEMS are also used in the glucometer, which monitors glucose in blood using a chemical transducer and delivers insulin on an as-needed basis using a micropump. A transmitter relays the information from the glucose sensor to the computer. An actuator is a device that converts energy into a motion or a mechanical energy. It is a mechanism by which a control system acts upon the environment. Some of the earliest form of actuation can be found in the Archimedes screw, which was one of the first linear actuators used to haul water from boats. Bimetallic strip converts thermal energy into motion using thermal expansion of the metal strips. This is a thermal actuator. In an electric motor, the transducer and an actuator work together to convert electrical energy to a magnetic energy into mechanical energy. This is an example of an electric actuator. At a screw jack, the rotary mechanical input is converted into a linear motion. This is an example of a mechanical actuator. Mechanical actuation can produce a rotational output with proper gearing mechanism. A hydraulic actuator consists of a cylinder or fluid motor that uses hydraulic power to facilitate mechanical operation. The mechanical motion gives an output in terms of linear, rotary, or oscillatory. Pneumatic actuator converts energy formed by compressed air at high pressure into motion. The piezoelectric actuators convert an electrical signal into a precisely controlled physical displacement. It is used in cryogenic vacuum environment. Just like the sensors and transducers, actuators too have a lot of application in the MEMS technology. Microthermostats and microvalves use bimetallic actuators. Electrostatic comb drives are used in MEMS like resonators, microengines, and gyroscopes.